Hey, so welcome everyone to the next edition of Myth on Times. Thank you all for coming or joining online. Today we have the pleasure of exploring a little bit about image segmentation with Barbora Planková and Hájek from Biano. And yeah, I'm gonna leave you to it. It's yours.
Yeah, thanks, Tondam. So today we're going to talk about binary image segmentation using synthetic dataset. It's a project we did at Biano AI for last 7 months. Biano needs maybe some introduction. So Biano is a company which is a marketplace of furniture and home decor, and nowadays we're switching slightly towards being something like a social network, because we found out that many people like to spend their time by decorating their homes. And for that, we have a feature in Biano called Biano Studio, where you can design your home rooms, or maybe just a corner or something. And for that, from the technical point of view, we need to know how to remove background from the foreground. I forgot to say that at Biano Studio you can put any image you want, but mostly you pick up from the products we sell in Biano. And from the machine learning point of view, when you want to remove background, you usually use semantic segmentation. So something about our problem domain. We have many products of different shapes with white backgrounds, sometimes with a shadow, sometimes without. With some sample backgrounds, and some stuff is simple and some stuff is difficult, like this one, which is a swing consisted of different shapes and in front of a quite challenging background. Sometimes, of course, we have bad images, as everyone, with text or some random images over that. And sometimes we have scenes. The products we sell are placed in a room with other decorations, and with some decorations that can be on or before the products we want to segment, right? So that's difficult. Of course, for semantic segmentations, there exist general purpose models like the unit family or mask RCNN, where also belongs Detectron from Facebook, or fully convolutional networks, for example. In our current production, we use a model belonging to the unit family, the UScornet, because it is a model that treats salient object detection. It first detects which of the items is the most dominant object on the image, and then it segments it. And we need it for the difficult images like the scene I showed you before. Maybe fun fact: UScornet was trained on not so many images, but it was good enough. So how does UScornet treat our data? For some data, it segments really well. This is a children's bed. But sometimes it fails weirdly. This is a chair, and it shouldn't be difficult, but it is for the model. And the general purpose models are especially bad for lamps. Because when you are a model and you are trained on things like cats, dogs, people, cars, and airplanes, and you have something with weird shapes and different colors glued together, you just don't know what to do about it. yeah, so hopefully I convinced you that we have quite unique domain and difficult for general purpose models. Therefore, we need to create our own custom data set, right? So when you're doing a segmentation, your data set looks like this. You have an image, and then you have to meticulously draw a map of the contours of the items you want to segment and spend the rest of your youth on it. So we thought, okay, let's not do that. And we thought it might be a cool idea to try to create a synthetic data set. When we looked into the literature, there is some work about synthetic data sets. Mostly they recreate the whole scene really artificially from scratch, by creating 3D models. I'm not gonna overview all of them, just the last one, because it somehow connects with our case. Here in this work, they created synthetic data set for industrial domain when they wanted to train various computer vision models of products placed on the shelves in a warehouse. So I'm going to show you how they created it. First, they photographed the item from all the different angles. Then they made a 3D model of it, and then they put a texture on it. So this is the first step to segment to have the item, and then place it on an. Oh, sorry, this is taken from the paper, but it's really of low quality. And they place it on a random scene. So like they have flying yogurts in front of a monument, or in front of a swimming pool, or in a cockpit, or in a train station. Yeah, why not? So back to us, how we did it. We don't want to do this. So what we did, as I said, we already have some segmentation model in production, and also we have at hand some simple segmentation models. So we thought, instead of annotating the segmentation by hand, let's make an annotation project asking first sampling the images, then segmenting it using three various models, and then ask annotators if any of the masks fit the original image, and if so, which. And this was done like this in a couple of days instead of like thousands of hours. So after that, we had some segmented items, and then, as in the paper, we placed it in a random scene. This is an empty room with some random products. So this is how our data sets looked like-ish. So now a cookbook, how to create a synthetic data set if you want one. First, you have to analyze your data, look for the features, patterns there are from the perspective of the model. Then make a strategy how to create the first iteration of the data set and perhaps simplify it. Then you implement it, and then you iterate, because you won't have your perfect data set at the first shot. So let's analyze the data. As I said, we have products of many shapes. There can be holes in it. There can be a composite of weird shapes and weird colors. There can be foul plays like this one. It is a pillow with a picture of motorcycle on it, but when you're a general purpose model, you segment the motorcycle because you have seen more motorcycles than pillows with motorcycles. You can have items with backgrounds, which are placed in the center or shifted to a side. There can be other images on your item, and there can be really bad images with bad light, also with some other things placed on them, and they can be blurred with the like here, blurred with the wall. So in in Biano data, majority of the items have a white background. Yeah, I said most of that. I haven't said that all the products, most of the products have shadows, and the shadows are of different shapes and different brightness and position. So let's do the data set. Let's make various types of backgrounds. Let's shift the position of the product. Let's make sure that the product stays within the image, which is kind of obvious, right? But when you're implementing it, you might forget about that. Let's give the product a shadow, and let's vary size of the product and size and shape of the shadow. So this is how it looked like. We decided for 3 types of backgrounds: a white noise background, some empty rooms background, and just a white background. White noise background is, of course, not present in Biano data, but we thought the white noise is the hardest thing you can give to the model, right? So when you train the model on the nastiest thing possible, then it should be brilliant on everything else, right? We shift the position. We have funny flying armchairs in an empty room. Why not? And for the shadow, we had two types of shapes. You can see that I won't describe it. So yeah, we had most of the data had white noise background. However, it kind of failed spectacularly when we, of course, we measured it on a validation and test sets, and the loss was low and everything was perfect. But when we applied it to data out of the synthetic data set, we found that the model learned that the product is that thing on the image which is not the white noise. So we had to scrap the white noise approach and do another iteration. So when not using a white noise background, let's use more empty rooms background. Previously, we had just a few empty rooms we downloaded from the internet, but now we wanted like 100 of them. And we thought, so let's use what we have at hand. Let's ask ChatGPT to create descriptions of empty rooms, and then let's use these outputs as prompts to a stable diffusion, and stable diffusion generated us empty rooms. Yeah, that's really clever and elegant. And it was Honda's idea. And the second model was better. It recognizes the beds, but there can be still some improvements. So as a third iteration, we analyzed the data by hand, and we looked where the model had most difficulties, and we added more data to cover those difficulties. And the third model was better. It's not perfect, I know, but it's much better than what we have now in production. And in Biano, we were happy enough about it, and we will use actually this model in production, and we plan to gather more active data when users are using the Biano Studio, and then retrain it in some time. Now, some small, fast technical slides. This project was more about dataset than anything else. And from the architecture point of view, we wanted to use something as cheap and fast as possible. So we experimented with a couple of simple segmentation models that are already implemented in PyTorch, and we arrived to feature pyramid network architecture, which worked the best. And we use efficient net v5 as backbone and ImageNet as the encoder weights, and that's all I'm gonna tell you about the architecture. I haven't talked much about this set, but we covered it a bit. You want to test on the real data, not the synthetic data, right? But then you don't want to segment meticulously everything, and then you have a bit of chicken and egg problem. So because we're lazy, we arrived to a compromise to have just not so many images in a test set, but the ones we thought would be of high quality. So we sampled 700 samples from the Biano data. And because at this stage we had already some models at hand, most of those images could have been segmented by one of the models, and we had to segment by hand just 200 of them, which took us like half a day, both of us. So not so much. Yeah, and how to measure it? One of the most common metrics in segmentation is mean accuracy. We looked into some other metrics, and we arrived to a structural similarity measure, which we thought it covers the problem better. This is some mathematical measure, mathematically created, and it should cover the structure of the data better than just comparing pixels. Besides these, let's call it, I don't know, statistical metrics, we also used some human annotation metrics. We asked the annotators the same thing we asked them at the beginning. We showed them the models, and we asked them if any of those segment the image, the original image, well enough. And of course, it's always a good thing to check your results visually. Before I show you our results, I'm gonna give myself a better lesson about machine learning. Richard Sutton wrote like 4 years ago that when you're developing you shouldn't develop a machine learning model which comes from your human perspective, and because the big general purpose models will beat you at the end. So we did exactly what he said we shouldn't have done, and I thought about this when creating this presentation, and so because we did this project during 7 months, and during this time there emerged 3 general purpose models concerning segmentation. So like there are general purpose models evolving, and did they beat us yet? One of them is Yellow V8. It was released this January, and it is a state-of-the-art model on detection, but also it does segmentation. So is it better than we are now? We actually thought about using it, but Yellow V8 uses a COCO dataset, which cannot read holes in the images. This is the best thing you can get to having a hole in something. So this is not good enough. And how does Yellow V8 treat our data? So it's not bad, but it's not good. It doesn't like the legs. The legs are always a problem. So like, yeah, but we're not beaten yet. The second one is more interesting. It's from the authors of the U-square-net, and it's a model that should treat really well these difficult images. So like if they can segment this bicycle with these strings and even have a ventil here, then we're doomed, right? They can segment the chair swing I showed you, right? So like, okay, thanks, we're out of the job. Yeah, the fun fact, they really built this image on a data set. They had not so many images, but of high quality, and it took them on average like 30 minutes to draw a mask in GIMP. And the record was to spend 10 hours of your time drawing a mask in GIMP. Thanks, but no thanks. So how does it do on our data? Simple data is beautiful, like always, right? Not so simple, but not so super challenging. It's not really good. And if I want to be nasty and put in the pillows with an image, it segments the dogs, and this one maybe not so well. It's okay, but like it's not like by a huge margin better than we are. So maybe we're still at game, and I'm gonna show you this this model at the results section. And the third thing, which was Vašek told me last week, it was released like really a week ago. A model from Meta, segment anything. They trained it on 1 million images with 1 billion masks. So yeah, that should be good, right? And how does it work? It automatically segments everything it sees on an image, and it has a really great user interface. You can point what you want to include and what you want to exclude from the segmentation. And if I prompted it enough, it segmented data well-ish. And this is our favorite bet. When I prompted it like 6 times, it really did segment the bed better than our model, but I had to interact with it. So at the first shot, it segmented, I think, just this rectangle. And if you have data with holes, which we do quite a lot, then sorry, can do. So now to our results. So maybe there is gonna be a general purpose model that is gonna beat us, but not yet. And to show you our results, as I said, we have 3 types of metrics: the normal, call it statistical ones. Then in this, our model worked actually well. Then we asked humans to evaluate it, and at that we arrived at the limitations of a small test set. So it was, they said our model is better, but not statistically significantly enough to show you the graph. And by a common sense view, of course, it was worse in some cases, but it did segment some classes really well compared to U-square-net. Mostly the ones which had white background but had many holes in it. We were really good at that. And now the most show-off slide. the mean accuracy and structural similarity metric for our model for the U-square-net, which is now in production, and for the this, which should be state-of-the-art model for semantic segmentation for really difficult data. And we're really better, and by a statistically significant margin, I would say. So, like, we're really happy about this, that we were able to beat the state-of-the-art model on our small playground, of course, of home decor images. And now to show you, the bat. So how does U-square-net segment this? It forgets about this backside of a bat as well as this, and I already showed you our result. Not perfect, but the best of what we have seen so far. So to conclude, we developed a method for creating a synthetic data set for semantic segmentation by sampling data, using pre-trained models to create a mask, and then some clever old empty room recreations. By doing that, we avoided the cumbersome manual creation of masks, and we had better result than the state-of-the-art model, which we were really happy about. And that's it. Thank you for your attention.